Basic electricity. DC circuits. Part 1. Series circuits. Electric circuits are used every day, whether you turn on a light, watch TV, or start your car. For the most part, electric circuits are taken for granted and used with little regard to how they actually work. In fact, the only time most people even think about electric circuits is when the lights go out.
To be successful in the electronics industry, however, you'll need to know more than that. To start, you'll need to understand the basic concepts that make up the elements of a circuit, that is, voltage, current, and resistance. This understanding starts with DC series circuits. Knowing how voltage, current, and resistance interact in a DC series circuit provides the foundation for an understanding of electric circuits. Without this basic knowledge, understanding basic electricity would be like finding your way in the dark.
Electric circuits provide a path for current to flow. All electric circuits consist of a power source, a conductor, and a load. The power source provides energy in the form of voltage. This voltage causes current to flow in the circuit along some type of conductor. The current flows from the negative side of the power source, along the conductor, through the load, and then back to the positive side of the power source. The load provides resistance to current flow. How much resistance depends on the purpose of the circuit.
The path the current takes from the power source to the load can be through one of three different types of circuits: a series circuit, a parallel circuit, or a series parallel circuit. In this program, you'll be shown series circuits. Two characteristics distinguish a circuit as being a series circuit. 1. There's only one power source, and 2. There's only one continuous path for the current to flow. This schematic diagram represents a series circuit with two resistors comprising the load. Notice that there's only one power source. In addition, each resistor is connected in the circuit so that there's only one continuous path for the current to flow. When resistors are connected in a circuit like this, they're said to be connected in series. Now let's look at how current, voltage, and resistance relate to each other in a DC series circuit.
To do this, you'll build a series circuit as represented by this schematic. As you can see, the circuit will have one resistor. In addition, an ammeter will be connected in series with this resistor. You'll build this circuit using a breadboard, a variable DC voltage supply, and a fixed carbon resistor. For our purposes, a 1% fixed carbon resistor will be used as the load in the circuit, as they are inexpensive and precise.
Finally, to measure and evaluate what's going on, you'll use two digital multimeters. One, as shown by the schematic, will be connected directly in the circuit, in series, to measure current, while the other will be used to measure both resistance and voltage.
To help keep an accurate account of your observations, have a notepad handy to record your measurements. Divide the notepad into columns, one each for voltage, current, and resistance. Since you'll be supplying the circuit with 5 volts, record 5 volts on your notepad for total voltage, or ET.
To begin, make sure the power supply is off. Then attach a test lead from the negative terminal of the power supply to the negative terminal of the multimeter. Then attach the negative test leads together. Remember, to measure current, the multimeter must be connected directly into the circuit, and polarity must be observed. Now select the 300 milliamp function. Before inserting the 1000 ohm resistor, first check it with your ohm meter to verify that it's within tolerance and not damaged. It's reading 1.0 kiloohms or 1000 ohms, which is exact. Record this reading on your notepad and label it R1. Keep in mind that although your resistor is rated at 1000 ohms, its actual value could vary. This variance is known as tolerance. In our example, 1% is the maximum allowable tolerance, which means that the actual ohm rating could vary plus or minus 1%, or 10 ohms, and this resistor would still be acceptable.
Returning to the circuit, insert the resistor's actual leads into holes for each of the 5 common contacts. Be sure to separate the leads by 5 or 6 holes for proper spacing. Next, attach the red positive lead into the positive terminal of the ammeter. After that, connect the clip end of the red lead to the right side of the resistor. Using a second red lead, attach the plug end of this wire to the positive terminal of the power supply and the remaining clip end to the left side of the resistor. On paper, use Ohm's law, that is, current equals voltage divided by resistance, to calculate the current flowing through the resistor. In this case, the voltage is 5 volts, and the resistance is 1,000 ohms. Therefore, the current should be 0.005 amps or 5.0 milliamps. Make sure the voltage adjustment knob is turned all the way down to avoid a voltage level that is too high for your components. Turn on the power supply now and adjust its voltage output to 5 volts. Turn on the ammeter. You can see that it's reading 5.0 milliamps. Record this on your notepad.
Now add this 1500 ohm resistor to the circuit. Looking at the schematic, you'll connect it in series with the 1000 ohm resistor. To do this, first check the resistor with the ohmmeter. It's reading 1.502 kiloohms or 1502 ohms. Since this reading is within a 1% variance from the 1500 ohm rating, that is plus or minus 15 ohms, this resistor is within tolerance. On a new chart, copy your previous R1 reading and your total voltage reading and record 1502 as R2, just under R1. Next, turn off the power supply and unhook the clip end from the right side of the resistor. Now, carefully insert the axial leads of this resistor into the breadboard. Remember, you're connecting this in series, so make sure to space the leads 5 or 6 holes apart and put the left lead of the second resistor in the same vertical line with the right lead of the first resistor. Using the ohmmeter, you can now measure the combined resistance of these two resistors by connecting a red clip lead to the left side of the first resistor and a black clip lead to the right side of the second resistor. As you can see, this measurement is 2.502 kiloohms. Remember, the measured value of the first resistor is 1,000 ohms. The measured value of the second resistor is 1,502 ohms. Now, the total resistance when measured is 2,502 ohms. This total resistance is actually the sum of the two individual resistances. Record this for RT.
Finally, to once again complete the circuit, connect the red clip lead to the right side of the second resistor. Again, using Ohm's law, you can calculate the current through the two resistors. In this case, the current equals 5 volts divided by 2,502 ohms, which equals 1.998 milliamps. Now, turn on the power supply and look at the ammeter. It's reading 2.0 milliamps. Record this for total current, or IT. Although this reading is slightly different from your calculated value, it is well within tolerance. Also, notice that the total current has decreased with the addition of the second resistor from 5 milliamps now to 2 milliamps.
Keep in mind that slight variances can occur between the calculated and measured values because of the tolerance and stability of the various components. Going back to our circuit, you can now add this third resistor rated at 2,000 ohms. Looking at the schematic, you'll add it in series with the first two resistors. Again, first check the resistor with the ohmmeter. It's reading 1,998 ohms, which is within a 1% tolerance. On a new chart, copy your total voltage reading, 5 volts, and your R1 and R2 readings of 1,000 and 1,502 ohms respectively. Also, record 1,998 ohms for R3. Next, Turn off the power supply and insert the axial leads of this third resistor into the breadboard. Remember to space the leads 5 to 6 holes apart and to put the left lead of the third resistor in the same vertical line as the right lead of the second resistor. Using the ohm meter, measure the total resistance of the 3 resistors by connecting once again the red clip lead to the left side of the first resistor and the black clip lead to the right side of the third resistor. Your reading is 4.500 kiloohms or 4,500 ohms. The measured value of the first resistor is 1,000 ohms, the measured value of the second is 1,502 ohms, and the measured value of the third is 1,998 ohms. The total resistance is the sum of the 3 individual resistances, which equals 4,500. Record this for RT. Using Ohm's law, you can again determine total current. Total current equals 5 volts divided by 4,500 ohms, which equals 1.1 milliamps.
Turn on the power supply and look at the ammeter. It's reading 1.1 milliamps. Again, record this on your notepad. Notice the current has again decreased with the addition of the third resistor, from 2 milliamps when 2 resistors were in circuit to 1.1 milliamps, now with 3 resistors in circuit. Now, measure the current between the first 2 resistors in the circuit. To do this, first turn off the power supply. Next, disconnect the ammeter's red positive lead from the third resistor, and disconnect the ammeter's black negative lead from the power supply's black negative lead. The ammeter is now out of the circuit. To once again complete the series circuit, reconnect the power supply's black negative lead to the right side of the series circuit. Now, open up the circuit between the 1,000 ohm and the 1,500 ohm resistors. To do this, lift the left side of the 1,500 ohm resistor out of the common group of 5 and reinsert the axial lead into a group of 5 below the center canal in the breadboard. This will ensure the proper separation of these 2 resistors. Now, take the red positive lead of the ammeter and connect it to the right lead of the 1,000 ohm resistor, and take the negative black lead from the ammeter and attach it to the left axial lead of the 1,500 ohm resistor. This will complete the circuit once again. Remember, to measure current, the ammeter must be connected directly into the circuit, in series. Now turn on the power supply. Notice that the ammeter is reading 1.1 milliamps. This is the same as the total current. If you repeat this procedure for each resistor in the circuit, you'll discover that the current through each resistor would be consistent.
3 conclusions can be drawn from this demonstration. 1. Total resistance, RT, in a series circuit is equal to the sum of the individual resistances. 2. As resistance increases in a series circuit, current decreases. And 3. Current is the same through each component in a series circuit. Now let's check the voltage in this series circuit. A potential difference exists at only 2 places in a series circuit: at the source, known as the voltage rise labeled ET, and at the load, known as the voltage drop labeled ER. Several resistors in a circuit would be labeled ER1, ER2, ER3, and so on. Use your multimeter to measure the individual voltage drops. Start with the first resistor, which is ER1. Make sure the multimeter setting is on DC voltage. Then connect the red positive and the black negative leads to the left and right axial leads respectively of the first resistor. The meter reads 1.113 volts. Record your answer. Measure the voltage drop across the second resistor, or ER2, by moving the red and black leads from the first resistor to the second resistor. The meter reads 1.675 volts, which is within tolerance. Again, record your answer. Finally, measure the voltage drop across the third resistor, which is ER3. The meter reads 2.222 volts. Record your answer once again. When you add these 3 voltage drops together, you get 5.01 volts, which is within tolerance. Notice that this is equal to the total voltage supplied by the power supply.
You've just demonstrated Kirchhoff's voltage law, which states that the sum of all the voltage drops in a series circuit must equal the supply, or total voltage. Stated mathematically, Kirchhoff's voltage law reads total voltage, ET, equals ER1 plus ER2 plus ER3. Returning to your chart, notice that the highest voltage drop occurs at ER3, which has the highest resistance, and the lowest voltage drop occurs at ER1, which has the lowest resistance. Remember, according to Ohm's law, voltage, E, is equal to current, I, times resistance, R. In a series circuit, the same current flows through each resistor in the circuit. That is, IT equals IR1 equals IR2 equals IR3. Therefore, since current is the same through each resistor, as the resistance increases, the voltage drop across the resistance also increases.
For example, R1 has a resistance of 1,000 ohms. The current is 1.1 milliamps. Therefore, ER1 equals 1,000 ohms times 1.1 milliamps, or 1.1 volts. When you measured ER1, the meter read 1.113 volts, which is within tolerance. R3 has a resistance of 1,998 ohms, and the current is again 1.1 milliamps. ER3 then is equal to 1,998 ohms times 1.1 milliamps, or 2.1978 volts. When you measured ER3, the meter read 2.222 volts. This verifies that Ohm's law is true for every component in a series circuit. Now that you've looked at the relationship between voltage, current, and resistance when loads are connected in series, let's take a look at power. For electrical circuits, power is the rate energy is delivered to a circuit, or the amount of energy or heat dissipated by the resistance in a circuit. It's measured in watts, which is the basic unit of power. 1 watt is the amount of power used by the load when 1 volt causes 1 ampere of current to flow through the load. The mathematical formula used to calculate power is power, P, in watts, equals the current, I, in amperes, flowing through the load, times the voltage, E, in volts, supplied by the power source. An easy way to remember this formula is to remember the word pi, which stands for P equals I times E.
Returning to the schematic, use the formula for power to determine the power dissipated by each component in the circuit. Start with the power dissipated at R1. Remember, power, P, equals current, I, times voltage, E. So P1 equals IR1, which is 1.1 milliamps, times ER1, which is 1.113 volts. P1 then equals 1.22 milliwatts when rounded. IR2 is 1.1 milliamps, and ER2 is 1.675 volts. Therefore, the power dissipated at the second resistor, or P2, is 1.1 milliamps times 1.675 volts, or 1.84 milliwatts when rounded. IR3 is 1.1 milliamps, and ER3 is 2.222 volts. Therefore, P3 is equal to 1.1 milliamps times 2.222 volts, or 2.44 milliwatts when rounded.
Using the formula for power again, calculate the total power, or PT, dissipated by this circuit. The total current, or IT, which is 1.1 milliamps, times the total voltage, or ET, which is 5 volts, equals 5.5 milliwatts for total power. Notice that this is the sum of the individual power dissipations. Therefore, the total power, PT, is equal to the sum of the individual power dissipations throughout the circuit. That is, PT equals P1 plus P2 plus P3. Let's stop here and review what you've been shown.
Number 1. A series circuit is defined as a circuit with only one power source and only one path for current to flow.
Number 2. In series circuits, total voltage is equal to the sum of the individual voltage drops. Total resistance is equal to the sum of the individual resistances. Current is the same through each point in the circuit, and the total power dissipated is equal to the sum of the individual power dissipations.
Number 3. Ohm's law is true at every point in a series circuit. In the next program, you'll apply everything you've been shown about series circuits to determine the voltage, current, resistance, and power using only a schematic diagram and mathematics.